Hello, good day, good day, good day. Now welcome back to Apostle 1 tutorial. Yes, Apostle 1 tutorial. Please consider subscribing to our channel or like our video. Yes. Now, today I am coming to take you through differentiation. Now we are done with the limit. I will solve more questions on limits, but I'm moving on to differentiation. Now, differentiation, we are coming to start with differentiation. We are coming to start with differentiating from the first principle. Now, differentiating from the first principle. Now, differentiation of a function, we are talking about a function, and function is y, which is equals to f of x. And this function y is equals to f of x can be in the form of a curve. Yes, a curve like this, or like this, any curve. It is a curve, yes. It's a curve in any form, yes. Now, the first principle, which is the same as the derivative function, is also called the derivative. Now, how do we talk about it? Now, is the act of using algebra to find the slope of a curve. Yes. Now, finding the derivative of a function is the same as finding the slope of that particular curve. Now, when I say slope, what does it mean? I'm talking about slope of a curve. Now, the slope is the same as the gradient. So it means we are looking for the gradient of a curve. Now, we will talk about differentiation, then we'll talk about general differentiation and a whole lot of things, yes. And so you have to, all the differentiation started from here, so you have to pay attention very well. So what we are going to do is I'm going to teach you how we can find the slope of a curve. Now, if I have a curve like this, the slope of a curve depends on the point at which we are talking about. Depends on the point of the curve. There is no way I can find the slope of this one. Unless we look for general formula for finding the slope of a curve, and that is what you are coming to look at it. We can't have one slope for this particular curve. This one is not like a straight line. If you have a straight line, you can easily find the slope. You differentiate, you resolve it to x and y, change in y over change in x, or difference in y divided by difference in x, then we get the formula for what? Formula for the gradient. But when it's a curve, how are you going to solve it? There is no way you can solve for the gradient without a straight line, because the gradient is the same as y2 minus y1 over x2 minus x1. That is the gradient. So we need to get 2 points on a straight line before we can find the gradient. Now, there is no straight line here, but we can generate our own straight line. Now, assuming I'm looking for the gradient of this particular curve, I can't find the general gradient of a curve, but I can find the gradient at any point on the curve. Then we use that one to derive the general formula for the gradient of a curve. Now, I can look for the gradient at this particular point here, and it will be different from the gradient at this particular point because the values of x are different. It will be different from the gradient at this particular point. So if I'm looking for the gradient at this particular point, I need to get a straight line like this. And what's the meaning of this straight line? This straight line is a straight line that is tangent to the curve. Yes, if I'm looking for the gradient at this particular point, I look for a straight line. Now, this straight line is tangent to that particular point I'm looking for. So the gradient of this particular curve, unless we get a straight line, and that straight line is tangent to the curve. You see, this one is tangent to the curve, it touches the curve. So it means that the slope of a curve is the same as finding the slope of the tangent. You need to keep it very well. The slope of a curve is the same as finding the slope of the tangent. So when you have a curve like this and you ask to find the gradient or the slope of the tangent, is the same as finding the slope of the curve. Yes. Now let's look at this. Let's look at how we can find it. Now don't forget that finding the gradient or the first derivative, we call this one to the first derivative. Finding the first derivative is also the same as delta method. We call something called the delta method. So when they ask you to use the delta method, they want you to go through the first principle, but I'll teach you how to use the delta method to solve. Yes, delta method. Now let's see. Let me consider a curve. Pay attention very well. Now let me consider a curve. This particular video, I want to give you a full explanation on the first principle, because you need to lose the limit of a function. You have to go through a lot before. Now let's see the first principle. Now let me consider a curve. Let me consider any curve at this particular point. Now this is the curve. The curve is y, which is the same as f of x. And you know this particular one is the x-axis. Now this one is the y-axis. So this is our curve. Y is equal to f of x. The curve can be in any form, but I'm using this one to represent a curve, which is y is equal to f of x. I'm using plenty terms, so you have to follow very well. Now let's look at something. Before I can locate any point on a curve, this one, I need to get a value of x and its corresponding value of y. You get it? So let's say if I locate here as x is equal to a, then this one, I'm going to get a corresponding value of y. So if y is equal to f of x, then I'm looking for s is equal to a. So it means that we are going to get f of a because the s is a. Now if you have another point here and here at this particular point, s is equal to b, then I can get the corresponding value for y, which will give us f of what? B, because the x is b. So corresponding value give us f of b. That is our y, f of b. Are you following? I can label this one as y is equal to f of a, and this one will be y is equal to f of b because s is equal to a. Here s is equal to b. Please follow carefully. Follow me very well. Now, let me consider this particular curve. Before I can find the gradient of this particular curve, I need to look for a particular point on the curve. Then I'm going to find the gradient of that particular point on the curve. And before I can find the gradient of that particular point, I have to look for a line that is tangent to that particular curve. But let me relax, and then you need to get a better understanding for this. I want you to get a full understanding on this one. Now, so let's see. Now let me consider a point A. I'm going to consider a particular point A on the curve, and I'm going to find the gradient of that particular point A. Now let's say a point A has x value x. Now this is the x value. I'm talking about this particular value is its x. So which means from here to here is x. If here is x, it means the x is from here to here. Now what will be its corresponding now let me bring the point here so that to be simple. Now let me consider a point here x. So which means from here to here is x. From here to here is x. Now what will be its corresponding y value? This is the function f of x. So the y value will be here. So this will be our y value. Y value, that is f of x. F of x because the s is the same as the same x. It's the same as the same x. Now let's say this point is A. Now a point A has x and y value. You get it? Follow closely. Now what is the A? What is the x? The x is still x. What is the y? The y is the same as f of x. So I can say that this particular point A has a point x and then f of x. So this particular point A, here point A, has a point x and then what? F of x. Why x and f of x? The x value here is x, and the y value here is the same as f of x. The y value is the same as what? The corresponding y on the y-axis, which is f of x. Follow closely. Follow closely. Now, let me consider another point on the curve because we are looking for the gradient. Let me consider another point on the curve. So let's say we have a point here. And it's supposed to correspond to the corresponding y value. Let's say this is the y value. Now let me label this particular point B. And this point is supposed to contain x and y because every point contains x and y. Now, at this particular point, let me identify s value here. Now, this part is x. What will be here? Before I can get here, here's supposed to be from here up to here, right? Yes. Now, if from here to here, let me label from here to here as h. Let me label from here to here as h. That is the distance from here up to here as h. As h. Then what will be this particular point? What will be this particular point? This particular point will be the distance from here up to here, right? The distance from here to here will be the x, because from here to here is x. Here is the same as x, and here is h, so here will be s plus h. Because I'm looking for from here to here. Here is x, here is h, so this side will be s plus h. Don't forget that this s is the same as here, but it ends at this particular point. So the whole of this one is x. So this point here will be x. Now let's say from here to here is h. So this particular point here will be h. Now what will be the corresponding y? The corresponding y. The corresponding y here will be y is equal to s plus h. Why s plus h? Because the s value here is h. You get it? I hope you are following. I can also write this one in a different way so that you understand. Now let me label this one as my y1 is equal to f of x. I can label here as my x1, which is equal to x. Then here will be my s2. Here will be my s2. s2, which is equal to x plus h. Then I will say that f of s is the same as f of s1, which is the same as x. And then f of s2 will be here. So here is supposed to be s plus f of s2. You get it? And s2 is the same as s plus h. Just like I'm just simple like that. I can use s2 or something like that because the s2 here is the same as from here to here. You get it? Yes. Now, so I'm going to label this one x1, then the corresponding here will be y2, because we are coming to find the gradient. Now, let me draw a straight line from A to B. Okay, let me identify this one. So our point x here means our point x is our s2, y2, right? I will clean this one because I'm not going to use s2 and y2. Our point here will be point s2 and then what? y2. Now, what is our s2? Our s2 is from here to here, which is the x plus h. That is s plus h. So our b will be s2, which is x plus h. And then our y2. What is our y2? Y2 is the same as f into bracket s plus h. That is f into bracket s plus what? S plus h. Right? So I'm going to use that one, right? I'm going to use that one. So our point B will be the same as x plus h, x plus h, comma, f of x plus h. So this is our x2 and this is our y2. Yes, I hope you are following. Now, I'm going to look for the gradient of AB. Normal gradient of AB. So I need to draw a straight line from A to B. I'm going to look for the gradient of AB, not the curve. This one is the gradient of AB. Now AB becomes a chord because this one is a curve. So I'm looking for the gradient of the line AB. Now before I can get the gradient of the line AB, here is A, here is B. I need to resolve it. So which means I can resolve it like this. Where from here to here will be the difference in y. And then from here to here will be the difference in s. Now what the difference in s is the h. That's the h. Now what will be the difference in y? Difference in y means you have to subtract the y2 minus y1. Right? Right? whilst the difference in x means the x2 minus x1. You see, when you subtract the x2 minus x1, you're still going to get the h. But I've allocated here as h, so that's why I'm writing the difference in x to be h. The difference in y is y2 minus what? y1. Please follow closely. Follow closely. Now I'm not looking for the gradient of the tangent now. So let's look at something. Gradient. Now let me write slope rather. Slope of AB. You know, slope of AB will be difference in the y over difference in what? Difference in x. Difference in y is the same as y2 minus y1 over difference in the x, which will be the same as x2 minus x1, but the difference in x is now h. You understand? The difference in x here is h. So let me write difference in x. Now what is my y2? y2 is the same as f of x plus h. This is our y2, f of x plus h. Now minus our y1. What is our y1? This is our y1. Our y1 is f of x. So that is f of x. Now all divided by difference in x. Now the difference in x is h. Difference in x is h. So this is how we can find the gradient. You know, these ones are functions, so you know how to deal with functions. Yes. How? Are you following? Yes. Now, so we have our slope dy over dx. Now let's look at something here. Our slope is dy dx, which is now f of s plus h minus f of s all divided by h. Now, this one will give us the slope of this particular straight line, any point on this particular straight line. If it is here, the gradient will be this. If we have a point here, the slope will be this. If I have a point here at A, the slope will still be this. Now, specifically, I'm going to, because this one is a curve, I'm going to look for the gradient at A, at the point A here. So, what is the gradient at A? It means I need to draw a straight line tangent to the curve at A. I told you that when you have a curve like this, and I want to look for the gradient of this one, a point on the curve, I need to draw a straight line which is tangent to the curve. I need to draw a straight line which is tangent to the curve, which touches the curve at that particular point. So let me draw a straight line here, and that straight line is supposed to touch the A because I'm looking for the gradient at A. Now, so the gradient at A here, I need to draw a straight line that will touch A. So this will be my straight line. Now this straight line is touching A. And what is A? This one becomes the point of tangent, or the point of tangency, or the point of contact. So it means I'm coming to look for the gradient of the tangent. This one is the gradient of the line AB, or the chord AB. So this one is the gradient of the chord AB, or the line AB. I'm coming to look for the gradient of the curve at the point A, because A is exactly on the curve. So I'm going to look for the gradient at the point A. Now, before I can look for the gradient at the point A, I have to consider this particular curve, because f of x. Now, the value of x will change. Now, the gradient at this particular point will be the same as this at here. Will be the same as this. So let's see. Let me introduce our limits. Let's say we are looking for the gradient that is at any point on the curve. So let's say the point is from here. If the curve is at this particular point, what will be the value of h? The h will change. From here to here is h. Now when I talk about here, the h will be small, and we can get a corresponding y value, right? Now at the moment we are looking for the gradient on a particular curve, on this particular curve. Now as the curve is moving up to the point A, now when it is moving up to the point A, at this point A, here is the same as x, right? Now if this place is x, what will be the h value? At this particular point, the h value will be 0, exactly 0. At this particular point, the h value will be exactly 0. That is, when the point is here, the h will be 0 because the h starts from here to here. So at the x, h will be 0. Now, so since we don't want h to be 0, and we are looking for the gradient at the point A, which means that we have to talk about a situation where the line will be approaching here, and here is 0. So as this straight line moves from here to here, the value of h will be approaching 0, because when the h gets to this place, it will be exactly 0. When the h gets to x, it will be exactly 0. You get me? So we are going to look for the gradient as the h becoming very small, approaching here, the s value. That is when the h is approaching 0. When the h approaches 0, it means there's not going to be any straight line here. There's not going to be any point like this. The h will be 0 at this particular point. At the s, h will be 0. And the moment I say let h approach to 0, which means I'm giving limitation to the h. That is this particular h approaching 0. So let's move on here. Now, so let me talk about the limit when, okay, let me continue from here. Now let me talk about the limit when the dy dx over dx is approaching, where the h is approaching 0. The h is approaching 0. Now this one will give us the same as what? Which means I have to introduce the limit to this particular tuntun, which means you're going to have a limit of the whole of this one. And the whole of this one is the same as f of x plus h minus f of x over h, where the h may be approaching 0. Where the h will be approaching 0. The h will be approaching 0. Now, the moment the h will be approaching 0, we are going to get the line here. The moment h is coming to this particular point, we are going to get a gradient at this particular point. And the gradient at particular point A will give us the gradient from the first principle. So, which means the whole of this one becomes, when the limb of h approaching 0 is equal to this one, then this one will be approaching something called dy dx. Now, what's the meaning of this one? This is the same as the dy dx, which is the same as limb of the change in y over the change in x, where the h is approaching what? Where the h is approaching 0. So our dy dx is equal to the whole of this one, which is this, which is limb of f of x plus h minus f of x all over h, where the h is approaching what? Where the h is approaching 0. And this is what we call the derivative from the first principle. So if I have a y is equal to f of x, and I want to differentiate the y, it means that I have to find the differentiation of the y with respect to the x. We call it dy ds. We call this one dy ds, or y with respect to x. It's the same as differentiating of the x. You bring the prime here. So when you bring the prime here, it shows first derivative. We're going to talk about second derivative. So we are going to use this one. If the function is given in the form of y, we can make it dy ds, which is the same as this, or f of prime of x, which is the same as this. So right now, what you have to keep in your head is that for the first principle, the slope of this particular curve, the slope of dy dx, if we have y is equal to f of x, then differentiating the y with equal to x, which is the same as f prime of x, we are going to use both. It's the same as limb of f of x plus h minus f of x all over h, where the h will be approaching what? 0. Where the h will be approaching 0. So this is what you have to keep in your head. This is what you have to keep in your head. Now, so when we are differentiating, or we are finding the first derivative, or we are finding the gradient of that particular function or a curve using the first principle, this is what we are supposed to use. This is the formula we are supposed to use. So this is the proof of the first principle. Now, in the next video, I'm going to use this one to find the derivative, going through this process to find the derivative, or the first derivative, or the dy dx, or f prime. I hope you get me. So this is how we can prove the first principle. This is how we can prove the first principle. Now let me see you in the next video for examples on how we can go through this one to solve questions.